All right, we're going to talk about the concept of related rates. We're going to start with an example so we can see how this fits. A camera is located 50 feet from a straight road along which a car is traveling at 100 feet per second. The camera turns so that it is pointed at the car at all times. In radians per second, how fast is the camera turning when the car is 100 feet down the road? So now you got an example problem. Let's talk about strategies. All right, steps for solving related rate problems. First thing you have to do is identify the rates. Now there are two rates, and first of all, rates are what is changing. There's going to be a given rate. They have to give you some sort of rate, and then there's a rate that you want to find. There are often some things that are constant, unchanging, and it's usually useful to find some units. You definitely want to identify units, especially in your final answer. Step 2, identify an equation that relates the changing variable. This is sometimes the trickiest part. To do that, what you want to do is draw a picture is usually helpful, use similar triangles, use the Pythagorean theorem, or use dimensional analysis, which relates back to that units. After you've got that equation, then you're going to take the derivative with respect to time. That usually involves implicit differentiation. And be careful about your constants, because anything that was constant, its derivative will be 0. Then finally, you're going to substitute the values for the changing variables, solve and interpret, and don't forget your units on your final answer. All right, back to our problem. So I've taken the liberty of drawing some of the picture, and what we can see is we have a camera is located 50 feet, so this would be 50 feet from a straight road, and the car is traveling at 100 feet per second, so this is 100 feet per second. The camera turns so that it is pointed at the car at all times. In radians per second, how fast is the camera turning when the car is 100 feet down the road? So we want to look and see how this angle theta changes as the car moves. So the car is moving, the angle is decreasing. All right, so we know this distance was 50 feet. We know the car was traveling at 100 feet per second, but we have to figure out what that represents. So that's how quickly this distance is changing. So let's call that distance something, so call that x. So that means that this is the 100 feet per second is dx dt, and it's getting shorter, so it should be negative 100 feet per second. All right, so now we know dx dt, and we know we want to know d theta dt. So d theta dt is what we want to know, dx dt is what we do know. We need an equation that relates them. So we got to look at our picture, and the thing that comes to mind is the only thing we know when we deal with angles are trig functions. So if you look at this, you can say, well, here's theta, and from that we can see this is the side opposite of theta, and this is the side adjacent to theta. So that reminds us of tangent. The tangent of theta should be equal to x over 50. And I can plug the 50 in because the 50 is not changing. So it's a constant. So the next question we get is, wait, we were looking for when it was 100 feet down the road, so can I put 100 feet down in there? And the answer to that question, when you want to see if you're going to plug a number in, you've got to say, is that number changing? If that number changes, or that value changes, that dimension changes, You can't plug it in until after you've taken the derivative. All right. Since as the car moves, that 100 feet will change. That you can't plug in now. So our next step is actually to take the derivative. All right, so we're taking the derivative. The derivative of tangent is secant squared of theta. Now remember, we're taking the derivative with respect to time, because it's 100 feet per second. Those are time units. That's what these are all going to be. So you have to remember to use the chain rule, and this is the most common thing that people forget, is now you need to multiply by d theta dt. And then equals the derivative of the other side here, that's 1 over 50 times dx dt. All right, and I solved that for d theta dt in terms of our variables. I haven't plugged anything in. I just used the fact that secant squared is 1 over cosine squared, and then multiplied by cosine squared. All right, now we've taken the derivative. Now it's time to plug in all of our numbers. And this is when I use what I call a little snapshot picture, which I'll draw right here. At the snapshot picture time, that's the one instant when we know this is 100, right? This has always been 50. This, of course, is right angle. We can now plug in our pieces, and we still know that dx dt was fine because that's what the car was traveling. So if we plug those in, now I plugged in, the only thing is I don't know the cosine. The easiest way to do that in this case, and without using the calculator, would be to find the length of this hypotenuse using Pythagorean theorem. And now, if I'm using the Pythagorean theorem, I found that side, I can now plug in, because cosine is adjacent over hypotenuse, so this would be 50 over the square root of 12,500. And that's squared, because it was cosine squared. All right, so cleaning that up and simplifying, we get d theta dt is negative 2/5. And so the only thing yet to talk about is the units. Now I did add the units into the original equation, just to talk about where they came from. The 50, remember this 50 came from, that was the 50 feet of this side over here. And this 100 was the 100 feet per second. So that's came from the velocity of the object. And inside of here, hopefully you know that the cosine ratios won't have any units, but if you're not sure, they'll still work out, because it would have been this 50 feet again over, this would have been in feet. So feet over feet. I didn't put those ones in, but they would have canceled. And now if we check that, we can see that what will happen up here is this feet would have canceled with that feet. And if you would have put these feet in, I'll put them in here just for giggles. And now that and that will reduce. And so the only units we're left with is seconds. So this would have been per seconds, or 1 over seconds. And that agrees with radians, because remember, radians really isn't a unit. It's a measure of how many radiuses. So there's our final answer.